take on some online classes, some using some platforms, and some midterm exams already have been taken, and end term exam will start in mid-July. I mean, in the first week of July, next week, in fact. So online exam will take place for end sem, and then final year evaluation will, I think, will be on the past performance as well as these exams. But lab exam is somewhat difficult to take. I don't know. So based on the biology or something. Are you thinking of any virtual lab for the next semester or anything?
No, say what we have decided for the next semester, we will have some theory class or online theory class, and the lab will push it to the next semester.
Next semester, not this semester.
Okay. Not the coming semester. Following semester we will arrange it like this, because we thought that we will not compromise that lab course.
So has the government declared anything that university or school or colleges will be closed for such a long time,
Up to 31st July, MHRD
here also 31st July.
That's fine. We had our entrance exam scheduled in the first week of August.
That will be online.
But I am not sure. No, because it was initially thought, online, offline, everything was tried, but I don't know whether that can be implemented or not. Now things are, basically pushed to September and like this. Because according to the latest picture that IIT and others, it's late November or early December is when they are going to start the session.
Yeah, JEE and all these exams have been postponed.
Yes, exams are September, and the admission, counseling, all these things, so they will start in November, early November or in December. That's it.
So that means this semester will be gone, actually.
This semester is gone.
Next semester is almost gone. Yes. Yeah.
So what about your admission? How are you arranging admission?
Admission is going on online, and few students are coming to see the campus and all this, So counselors and admission cell is there working, and that different, the administrative positions, people are working administration, they are coming. So it's a big campus. You have seen that campus. So
I have seen.
everyone has some sufficient room, space and all this. So they're taking all kinds of precautions and they're coming. So few students are coming with their guardians and they're looking at the campus and all this. So admission is going on. But, until unless the higher results are published, and according to the government, West Bengal government, results will be published within July, 31st July, they say. So after that, I think they will decide. And usually every year, a lot of students go outside West Bengal. I don't know what happens this year because of this pandemic situation.
We don't know.
This is another case. So. Other university also they are taking exam based on like Calcutta University Presidency as well as Jadavpur. They are taking based on the previous exam only, previous code and also some assignments there. That's all. So one thing is difficult, that is how to set up a virtual lab. That is the most challenging thing, Even if the students get the internet and all these, you can take some theory classes, but what will about the lab?
So there is no substitute, they should learn how to hold the burette, pipette, Say.
Chemistry is difficult.
It's very difficult.
So our Professor Bimal Sarkar is here, right?
Yes, sir.
Okay.
Actually, sir, YouTube live, it is taking some time. So I just waiting just 2 minutes, sir. It will finish.
Okay. Anindo gave a lecture here.
When?
I think 1.5 months ago, I guess.
I see. Okay.
And then Professor Lane came,
and
another faculty from IIT Roper. He's told something about.
I see. So you are holding it regularly.
Yeah, more or less all the departments. So that we have science departments, we have physics, chemistry, mathematics, geography, and environment science and psychology. So more or less every day or every alternate day we are having some webinar. Other schools are also taking webinars. And,
এখন তো আমাদের মিটিংও এইভাবে হচ্ছে।
হ্যাঁ, সেটা খুব জানি না কি
সবকিছুই মানে আমাদের যা কিছু সব এখন কি হচ্ছে, ফ্যাকাল্টি মিটিংও করেছে। এবার ফ্যাকাল্টি মিটিং মানে
সেটা এখানে হচ্ছে।
হেডস ডিনস এগুলো তো হয়েছেই, প্লাস এখন ফ্যাকাল্টি মিটিংও পর্যন্ত আমাদের সবাই আসতে পারবে কি পারবে না, অনেকজন সিট থাকে, ফলে এইসবই করতে হচ্ছে।
তোমরা কি প্ল্যাটফর্ম ইউজ করছো, জুম অর এনি আদার?
আমরা গুগল মিটটাই আমাদেরকে রেকমেন্ড করি।
গুগল মিট। আচ্ছা,
জুম আমরা করেছিলাম, কিন্তু আবার সেই কি বলছে নানা রকম ডেটা পেতে।
গুগল মিট ইজ ফাইন, না?
Google Meet is fine. Microsoft Team is also good.
Microsoft Team, yeah.
Some PhD viva exam conducted through University of Science for the student. That was through Microsoft Team. And WebEx also we have explored. So we have explored everything. This is the time, because pre-PhD viva and a PhD viva in a school, there are a lot of activities. So let us try everything and let us see some.
Yeah, main problem is school teaching. I don't know how they have to manage. City they are okay, but in Mopasal area and village area, how many students they have these internet connections, or so that school teaching is suffering. Will suffer a lot.
Many people come from rural background, particularly
that is why
it is like ours. So it's a bit difficult.
Yes. Orpon?
Sir, now we can start, sir.
Yeah, host, you are allowing people?
Yeah, we are allowing people, sir. There is some problem in YouTube live actually, but I'm working on it.
No,
but we can start.
In Zoom?
Zoom, there is no problem, sir.
1 second. No, that Reena is not able to connect. Reena Ghosh. Let's see. I sent us. Can you see this? No. This also? Internet is nothing. Listen from.
প্রথম দিকে এরকম অনেক টিভি প্রবলেম থাকবে। নেটওয়ার্ক সবকিছুর উপর নির্ভর করছে, মানে
our network in West Bengal, we had a tremendous problem when we had the home fan. After home fan, there are about 17 days we have a lot of problems. Even we couldn't make phone calls. Phone Vodafone was totally off. Then we were very much anxious about holding the lecture of Professor Lane, because he was 29 just after 9 days of the home fan. So however, that particular day it was okay. So about 1,200 participants were there. So that went very well. But before that, it was a very horrible time. We had a horrible time of internet connection and phone connection. So, Umfan is a lot of damage. It has done a lot of damage. West Bengal, particularly Kolkata, has suffered many things.
Yeah, I think previously you never had something like this.
No, not in last 100 years or something.
Because everybody was telling nothing will happen to Kolkata. It will Just
Yeah.
go through some other region. That was not the case this time.
Every time it goes to, it went to Bangladesh or something, but this time just on Kolkata, comes through Digha, Mednipur, and then straight away to Kolkata and Sundarban. Arpan, should we start?
Yes, sir, we should start. But YouTube have some
Yeah.
problem. No problem, sir. We can start from here.
YouTube কি হয়েছে হচ্ছে না?
ইউটিউবে স্যার কোনোভাবে লাইভে যেতে পারছি না, সবকিছু ঠিক আছে স্যার, লাইভটা কি যে হচ্ছে।
লাইভ মতো কি দেখাচ্ছে না?
এটা চলে গেল না? How many students? I think you have 7 or 8 students right now. You told it.
7 now, but 3 will go this year. Go out.
And postdocs? You have postdocs?
I have 1 postdoc. It's very difficult to get postdoc because the kind of organic, inorganic you ask for, you get 10, 20. But then something in our area, it's very difficult to get them. Now I have moved to some area where it's very, very difficult. Synthesis oriented, a lot of people are there. And very difficult.
So this company that is coming up with the vaccine is in Hyderabad, right? That's what people are saying.
Yeah. But I don't know how good, because all other, all companies outside, they are saying it's very difficult, it's not easy. But
within 15th August, it's not possible. I don't know that will be not possible.
I don't know how it is possible because.
Yeah. I have students who is a very good scientist in cancer research in Texas. He was telling that, sir, early January or in January, probably the date you can expect in USA. Late December, early January in USA. Then, India maybe, take some other time, some more time. That's the Oxford group, mainly.
Sir, we can start now.
Sure.
It's solved, sir.
Okay. Start then.
Yes, sir. Welcome our honorable speaker, Professor Onoy Samanto, Dean, School of Chemistry, and J.C. Bose National Fellow, and he is also Fellow of all the National Academy of Sciences, FNA, FNSC, FSC, and he will going to talk today that Perovskite nanocrystal, photoluminescence, and charge carrier dynamics. Before going to the speaker, I would like to invite our Honorable Dean Sir, Professor Bimal Kumar Sarkar, who is the Dean of School of Basic and Applied Sciences, Adamas University, to speak something regarding today's webinar. Sir. Dean Sir.
Professor Sarkar.
Sir. Sir.
Professor Sarkar. Bimal sir.
স্যার মনে হয় বেরিয়ে গেছিলেন কোনোভাবে, বাট ঢুকে গেছেন।
ঠিক আছে। Bimal sir.
Now he's.
Sir, sir, please, sir, it is your turn. Sir, please tell something.
Welcome address.
So, It's over to me.
Yes, sir. It's over to you, sir.
Okay. So it's a very nice moment and also a pleasure for us that today the Department of Chemistry, School of Basic and Applied Sciences, is organizing the webinar Perovskite in nanocrystals, photoluminescence, and charge carrier dynamics. Our speaker is very eminent professor, Dr. Onumoy Samanto, Dean School of Chemistry, University of Hyderabad. So, sir, it's our pleasure and honor that you have just raised the occasion, and your speech will be a very good way and also very informative for us. And it's very nice that today the audience is also very just eager to listen and to hear from you. And it is really very helpful, a very common platform where the all chemistry persons, not only chemistry, even from physics, natural scientists, I believe that scholars, scientists, and students, faculty members are here in this platform, and it's good opportunity for sharing their understanding and knowledge, and also to know, most importantly, the new way of finding the different properties, explore the perovskite nanocrystals. And it's our pleasure that today this webinar will go to end with a very big success, and it will be importantly very informative for us. So I wish all the big success of this 2 days webinar. Thank you very much.
Thank you, Professor Bimal Kumar Sarkar, sir, for your nice introduction and welcome to our speaker. Before handing over to our today's convener, Professor Sanjeev Ghosh, I wish to tell you regarding the little bit about our Department of Chemistry of School of Basic and Applied Sciences, Adamas University. We conduct in our department, we offer the program BSc Chemistry and MSc Chemistry and PhD Chemistry, as well as we also offer BSc and MSc in Environmental Science, and from this year onwards. And we have 3 DST projects running by our faculty members, as well as we have 10 faculty members who all have the PhD and postdocs. And we have already organized 4 webinars, one by Professor John Maryland, Nobel laureate in chemistry, and another one by Professor Anindra Datta from IIT Bombay, another by Professor Anupam Majumdar from IIT Rupar, and now today one is none other than Professor Onoy Samanto. So I welcome all the participants, both in the Zoom as well as the who are live on the YouTube. There is some problem earlier in the YouTube, so we have created the new link, and you can enjoy the link. And the link has been posted in the past YouTube comment box also. So, and here one thing is that please mute all of yourself. Only speaker will share his screen, and don't write anything on the screen of the speaker because it hampers the speaker attention. As well as if you have any questions, you can write here in the chat box in the Zoom, as well as also you can write in the YouTube comment box, where we will all take up your question and we will sort the question and we will present it to the speaker, and our speaker will happy to answer the question. Another thing is that this video is not being recorded, and also after the finish of this seminar, the YouTube video will also be deleted, and also there will be a feedback form to all the registered participants, and I request all of you to please fill the feedback form and reply it to the email. And as soon as you fill the form, you will eventually get the. If you don't fill the feedback form after the seminar, then you will not receive any certificate. I again welcome our honorable speaker, and I welcome all the participants, all the listeners. And now it is over to our Professor Sanjeev Ghosh, sir, who is a professor of eminence from the Department of Chemistry at Adamas University.
Thank
Sir.
you, Arpan. Heartiest welcome to Professor Onunay Samanto, our speaker today, and Professor Bimal Sarkar, Dean, and all the faculty members of our school and other schools, and also all other participants who may be faculty members of different institutes or students or research scholars, because we have already, I think, 500 registered participants. So I welcome them all, first of all. And then today's lecture will be by Onunay Samanto. So I want to introduce a little bit about him. It will take long time if we, tell everything about him. Only thing I want to mention that I knew Onunay when he first joined Indian Association Cultivation of Science as a JRF, and I was there also. And I think we worked together for a little project. And I think I have a paper with him also, right, Onunay?
Yes.
Yeah. So after that, finishing his PhD, he went to Notre Dame Radiation Laboratory for his postdoctoral things, and then came back and joined in as a faculty member in Hyderabad University. And then right now, as we already mentioned by Bimal Sarkar and Orpon, that he's a internationally acclaimed scientist. He has received all the honors that is possible in India. Right, he's a fellow of the Indian Academy of Science. He's a fellow of the other organizations like FNA, FNSC, and West Bengal Academy of Science. And he is also a very coveted position holding, that is a J.C. Bose National Fellow. And he's a dean and also professor, senior professor of Department of Chemistry at Hyderabad University. And he's about his research, if I want to mention that he has briefly, I should tell that regarding his awards and recognitions, a lot of awards he has got, and he has visited many countries, I think almost all countries in the world, including USA. Mainly he has gone to Japan many times, I am sure, and then other places, all other places, including Singapore, Australia, and USA, of course, and there are other places. He has been visiting professor, visiting lecturer, and he has got all kinds of awards. And right now he has about 200 publications, 200 publications with a huge H index and citations number. Citations about 10,000 probably, I guess. And is very famous for his laboratory, which is ultra-fast spectroscopy laboratory. He is doing on single molecule spectroscopy, ultra-fast dynamics of various systems, like he has previously done solute and solvation dynamics in deep eutectic solvents. He has done a lot of work in I think ionic liquids. He got very famous. I think he's the pioneer in the field of chemistry and physics and spectroscopy of ionic liquids. And I think journals like Physical Chemistry invited him for some invited papers regarding ionic liquids. So he's famous for that reason also. But right now he's doing, I think, apart from single molecule spectroscopy various systems, he's now doing charge carrier dynamics and photoluminescence of perovskite nanocrystals, mainly, along with photoprocesses in DNA, including G quadruplex and motifs, I motifs rather. So with this, and I already mentioned, he has published huge number of papers, which has many citations. And I hope, as I know Onunay from very younger days, he's a very good speaker, humorous speaker as well. And we have a lot of funny time with him, lots of fun with him. And I think today's lecture will be no exception. Everybody will enjoy this lecture, and because he's a very lucid speaker, everybody can explain in a very lucid way. So with this introduction, I think it is time to invite Onunay to start his lecture, and we are all eager to listen to him, so I don't waste my time. So please, Onunay, you can start your lecture now.
Okay, thank you, Sanjibda, for the introduction, and also to Professor Sarkar for the introduction. Let me thank actually Adamas University for inviting me to give the talk. And this is the first webinar I am giving, formal webinar I am giving, really. I don't know how it is going to turn out to be, but let's see how it goes. I did not know anything. I had to learn how to share the screen. Now that's the first test.
Yeah.
And let me see how to
You
share
can
the
find
screen.
your, yeah,
Let
in
me
the
see.
bottom.
Files,
Yeah,
yes, files.
Hmm.
Files.
Share screen directly there in the bottom.
Yeah,
In the
bottom I have
bottom,
found. Now, let me see.
if the green light is there, the share screen you can find.
That I have found, but then just a minute. Just a minute. Just a minute. Now when I'm asking for,
Orphan, you want us to click the share screen, right?
Yes, sir. No
yeah,
problem.
I shared screen, but then
And then you also download your
basic. Just me. I have found. I have
PPT.
found. I have found.
Yeah.
I have found. I'm just
Yes.
sharing.
Yes, sir.
Is it
It's
okay?
okay, sir. Okay, sir.
Can you see?
Yes, we can see, sir.
My volume is okay?
Yes, your volume is also okay, sir.
Okay. Let me start. The title of my talk, as I mentioned, is Perovskite nanocrystals, photoluminescence and charge carrier dynamics. And I am from University of Hyderabad. It's a very new university. As you can see, it is founded only in 1974. It has not completed even 50 years. It has around 5,100 to 5,500 students, some 450 plus faculty, but it has a huge piece of land, 2,000 plus acres. 2,400 acres was the original land. Now some part of it is gone. And much of it, you can see, is very beautiful. They are left as they were, a long time ago. The pictures that you see, four of them are from the campus. You can see the Hyderabad natural rocks, the lakes, all are in the campus. This is called Peacock Lake. And just let me see one thing. What light? Yeah, you can see this. This is the Peacock Lake, and these are the natural rock formation, etc. And this university is recently recognized as Institute of Eminence. One of the 10 institutions which are recognized recently by MHRD, and University of Hyderabad is one of them. Well, this is, as I mentioned, that I am interacting with you in this mode. It's because of this COVID 19, novel coronavirus. Now that is caused by basically, SARS-CoV-2 virus. You can see this is the TM image, a beautiful image you can see. And this will not tell you about this composition, but what you see on the left side, this one, you can see, what actually is this RNA and the proteins and envelopes, etc. Let me not go into this. I wanted to say this because I'm because of COVID virus, I'm interacting with you in this mode. And also one of the reason is similarity is that if you look at these, virus sizes, their diameter is 50 to 200 nanometer. And the story that I am going to tell you is also about the nanoparticles. Now, virus particles are very small, you don't see them, but the particles that I am going to discuss with you, they are even smaller. You will see 7 nanometer, 8 nanometer, 10 nanometer particles. So, it shows that how important is these small particles, small things, don't neglect because they are very small, don't neglect. And before I go to my talk, I think I should tell you that, this is an extraordinary situation. For 3-4 months, we are doing literally nothing. All our activities, have come to a standstill. We are not used to this. We never imagined that, this is how things can become like this. this is very strange. And you have seen that, WhatsApp messages like, air is so pure, but still you use a mask. We have so much time, but we can't have a get together. There are problems. We have plenty of money. Those who have money, they can't spend it. And people, who don't have it, they can't earn it. Anyway, so before I go to the next slide, I have only one message to you. Be positive, but don't test positive, okay? Test negative. That should be the goal, okay? Stay safe, be positive, and test negative. That's the message. Now, we deal with electronically excited molecules. As you know, I am a chemist, and like all chemists, deal with the molecules and materials. Now, other chemists, normally, they deal with basically thermally excited molecules. But what we deal with electronically excited molecules. They're much more energy rich. Now, what we do with these energy rich electronically excited molecules, it is not the chemical reaction in which my interest is. Our interest is on physical aspects. Like, we want to know when you excite a molecule in the electronic state, what are the species that are created? Like, we are interested in finding out the identity of the transient species that we create. They are very short-lived. We want to basically characterize them, their through spectroscopy, and also want to study their dynamics, the rate at which they form, the rate at which they decay, etc. Now, there are many things that can form. The short-lived species can be excited state, conformers, radicals, radical cations, anions, etc. How do we study them? There are two techniques. The technique is this. When you deal with normal molecule or thermally excited molecules, the molecule is in this state, okay, here. But we are interested not in this molecule, but an excited molecule. So basically, you have to create that species. So we create that species. Once you create that species, how do you study that species? Say, if the molecule is fluorescent, that means it is giving some emission, then what you can do, you can record a fluorescence spectrum. So that way you can identify, this state, molecule here. But if the molecule is dark, that means it is not emitting, then what you have to do? Then you have to record an absorption spectrum. Okay? Like the way you do for normal UV visible absorption spectrum. The only difference is that this ground state molecule is always there in the ground state in large concentration, and you can record an absorption spectrum easily. But here you have to prepare the molecule, and the molecule stays there for a few nanoseconds or even shorter. So during that short time, you have to record an absorption spectrum. So that's the difficulty. And that is why, there are a lot of complications and sophistications, involved. Now, I'm not going to talk about molecules today. I have decided that I will talk today on semiconductor nanocrystals. Semiconductors, semiconductors, metals, semiconductors, insulators. They are classified based on the gap between the valence band and conduction band. And the molecules they don't have band structure, they have discrete structure like HOMO-LUMO. But semiconductors are like this. These are bulk semiconductors, as you can see. You have a valence band, you have a conduction band, and there is an energy gap. And this gap will determine at what wavelength it will absorb. But I'm going to talk about not these bulk semiconductors. I'm going to talk about, nanoparticles. Now, when you nanoparticles, what happens? When you reduce the size of the nanoparticles, like you have, when you just squeeze that particle, then you can, if you just, allow only 2 dimensions, that means 1 dimension you have basically constrained, then you have a plate kind of thing. But if you, suppress or constrain in 2 dimensions, then you get 1-dimensional thing. But if the particle is basically confined in all 3 directions, then you have what is known as quantum dots. That means dimensionless quantity. That means particle is confined in all directions. And so these are the particles. Now, when you go from a bulk semiconductor to nanoparticles, then this band structure is lifted. And that's what I am showing here. It's shown here also, but this is shown better here. You have a bulk semiconductor, you can see the band gap, But then when you reduce the size, as you can see, these levels which were merged, now they becomes discrete, and the energy gap increases. And if you make it further smaller, then energy gap again increases. So in other words, you have just one material, let's say cadmium selenide. Just by changing its size, what you can do, it's like you're making many molecules. And so you can basically create, so many colors. It's like having so many molecules. You can see that I have plotted the energy gap. This energy gap is plotted versus the size of the particle. And you can see their absorption band, varies drastically. And you can see their color, which is reflected. When the energy gap is smallest, then you have this color. And when the particle becomes even smaller, then you have this blue color. And that is what is shown here also, cadmium selenide nanocrystals. So this is typical of not just semiconductors, but semiconductor nanocrystals. This is how they behave. This is how they show the size dependence of their optical properties, absorption properties. And that's what you see the color. But I'm going to talk to you not about these chalcogenide quantum dots like cadmium sulfide or cadmium selenide. I'm going to talk about a new class of materials, the perovskites. You see, perovskites are not, new. The perovskite, calcium titanate is very old metal, okay, very old in substance, semiconductor. Now, I'm going to talk about halides. So calcium titanate was known, and that structure is labeled as, perovskite structure. And that is why any system having formula ABX3 and which shows, structure similar to calcium titanate are known as perovskite. Now, your formula is ABX3. Now, you can have your A can be an organic moiety like methyl ammonium ion, or A can be a basically inorganic. So this is called all inorganic perovskite, and this is called organic, inorganic, or hybrid perovskites. And this is the structure, irrespective of. You can see this, A species sits here. It's a cubic structure. You have, BX6 octahedra, and their corners are shared. So it's basically you have cubic structure, octahedral BX6 octahedra, like PBX6 octahedra will be there, and the corners, the halides will be shared, corner shared. That is how it will grow. And so this is the typical thing, cubic, PBX6 4 minus octahedra, and then this void is occupied by the cesium or methyl ammonium, which has no role really. Energetics will be governed by PB and X orbitals. Why they are important? Why suddenly they have come into the prominence? Because they have, I will tell you, they have broad and intense absorption bands, and which can be really manipulated by changing their size. The one thing is that, like all of the semiconductors, when you go to the nano dimension, apart from their intense absorption, they can also show lovely fluorescence color, very high quantum fluorescence, quantum yield. They can show variety of nice colors. As you can see, this is a 100 nanometer scale, and in which 1, 2, 3, 4, 5, 6, 10 particles are there. So each particle is 6, 7 nanometer size particle. So you can have really a variety of things. So because of the broad and intense absorption, it has some use. And because of its fluorescence, it has another kind of use, like LEDs, applications, light emitting diodes, lasers, photodetectors, etc. And because of intense absorption thing, it has use in photovoltaics. So this is how it became prominent. These halide perovskites are nanocrystals. They are very, very new materials. I'll tell you how new it is. Now, I hope you know that how solar energy is converted into electricity. And there are many ways. Normally we use silicon, silica basically as the semiconducting material. There are 2-3 different technologies, but these dye-sensitized solar cell is a third generation thing in photovoltaics, where a dye is absorbed on a semiconductor titanium dioxide. When light falls on the dye, it creates electron and hole. Now hole is quenched by iodide ion, and this electron goes through this, and you get electricity. This is solar, Gratzel's dye-sensitized solar cell. This is very, very popular. It started long back, and it was very, very promising, technology. Now, it is in this context, you have to appreciate the perovskites. Why? Because you see the visible dyes, they will absorb only in the visible region. You can see this is the total solar spectrum. Yellow one is solar spectrum. Some part, what reaches Earth is this red colored one because of oxygen absorption, water absorption, and carbon dioxide absorption. Some part is green. So red is what comes. Now, if I am using a dye, dye absorbs mostly in the visible region. That means it can absorb only 43% of the light maximum. That means to begin with, you are losing 57% of the solar energy. You can't absorb. So how do you expect to convert? So you never expect the efficiency of these dyes sensitized solar cells, to be more than, even considering that 43%, if you convert, you get 43%. I will tell you where actually is. Because it is not absorbing large part. So you look for a material which will have broad and intense absorption. And so that is given by perovskite. I will show you the absorption spectrum of perovskite. They absorb throughout the region and intense absorption. So that is the main attraction. Apart from that, there are other things, how the electrons and holes, etc., move in this material, etc. So those are finer details. Those are additional advantages. And using these materials in 2009, you can see first, solar energy conversion experiment was tried with methyl ammonium, lead halide, and efficiency was found to be close to 5%. Later, Gratzel also himself is left dyes. Now, Gratzel cells now mean again, perovskite sensitive solar cells. You can see this is a very important chart. It's complex because there are different technologies. I will show you the efficiency, cell efficiency as a function of, year, as the time progresses. I put one thing. This is basically first dye sensitive solar cell designed by this Gratzel. It has some efficiency, number is very less. And over a period of so many years, 1990 to 2020, it has reached only this stage. Very little progress, improvement. Then came the semiconductor quantum dots, cadmium selenides. You can see that they started around 2010, and then efficiency is close to 15%, 14, 15%. But perovskites came even later. You can see that it's given much later. And then it just, you can see the slope that will tell you, how it goes up. Now it's 25+% efficiency. You can see there is some flattening. That means the initial thing was very high. Now it's difficult to, improve the efficiency. We are hitting the bottleneck. Okay. So this makes you understand that, why perovskite is superior. Within a very short time, perovskite sensitized solar cells based on, Gratzel mechanism can give you an efficiency which no other material can give. That's one of the applications. And in addition, as I mentioned, I'm not talking about the other applications, fluorescence, etc. They are used in LEDs, etc. Now, what is our interest in perovskite? In our interest is that, I'm a photophysics person. I'm not going to make, design something. Our interest is basic. So what do you see is that, this is the valence band and this is the conduction band, and you can see the discrete energy levels. When I shine light, let's say this is the energy, I create a hole here, electron here. Now these, they are short-lived transient species. They will not stay there. The moment light is removed, they will come down. They will come down to the original state. They relaxes like this, and hole relaxes like this, and then they can have something like this, electron and hole, which are bound together. This is what is called exciton. And they can also get trapped in something called trap states. So there are various species. What are the species? My interest is that, what are the charge carriers? When I design a solar cell, basically electron has to flow from one side to other. Now, if I create electron and hole, immediately they recombine, you get nothing. So the whole idea is that we have to see that, they don't recombine. They don't come here and give fluorescence and then become same thing. So it is necessary to understand, it is necessary to take this electron and hole out, hot electrons. So basically our interest is that, what are the species that are created? What are the deactivation pathways, etc. Basically we want to characterize what the species are and their deactivation pathways. we believe that if we understand that, then maybe we should be able to control this recombination, etc., and then make more efficient processes. We are also trying some other thing. This is basically an intra-particle process. We add some other species and then try to extract the charge. That is one thing. And the generation and extraction of bi-excitons. Normally one photon creates one exciton, electron hole bound electron hole pair. But then can you create use one photon? But then can you create two bi-excitons? That kind of experiments. Can we create, instead of waste this energy waste, can we extract this electron, hot electrons, before it relaxes, so that energy loss is less. These are some of the things that we do. We also do photoluminescence of the perovskite is also a very important thing, and hence we try to find out when we synthesize the perovskites, we find that quantum yield is not very good. We try to find out what are the reasons for their low quantum yield, and try to identify the origin of the low quantum yield, and then try to improve by surface treating or doping, etc., to enhance their fluorescence efficiency as well as their stability. Now, to do this first part or the second part, or basically this charge transfer dynamics, if I want to see, we use two techniques. One is called femtosecond pump probe technique. I will tell you about this. And the fluorescence technique also we use. There we use ensemble measurements, conventional measurements. Also, we study single molecule fluorescence-based measurements like fluorescence blinking and correlation spectroscopy. Basically, I don't like to go into the details of the word. I like to give you a feel of our perspective. What is our goal? What kind of measurements we make, and to get what kind of information that we try to get. Okay, let me go to this. Now, how do you prepare? Preparation is standard. I don't have to do anything. Preparation is very, very straightforward. Okay. What is, it's basically cesium lead halide. You have a source of cesium and you take lead, halide. So it's called two precursor method. But then this is not a very good method, because if you see the formula, CSPbX3, lead and X ratio should be 1:3. But if you use lead halide as the source for both lead and halide, what you are doing, you are taking less halide. So they are basically halide deficient, and their quantum yield is not so good. So that is why there is another 3 precursor method in which we take lead for lead. For halide, we take one extra reagent, and then we can prepare these things in basically hot injection method, and we can prepare them. We can characterize them in a very, very simple manner. There is a third method available, which is known as anti-solvent precipitation method. That's not very good. It's you have a solution in good solvent and then put it in a bad solvent, and then you nanoparticles precipitate out, and there is very little control and etc. and qualities are not good. So that is not what is recommended for most of the things. And our synthesized nanoparticles, they look like this. For example, this is CSPb-Br3 and CSPb iodide. You can see their sizes we can determine in PEM. They're typically 12 to 17 nanometer. And you can see as we go from bromide to iodide through mixed halide, how they shift towards red. When you go to iodide, then it will be red for the same size particles I'm talking about. You can, in these particles, the absorption and fluorescence you can control, not by changing halide, but also by changing size. So not by changing size alone, which you can do for other materials. Here, by changing halide also, you can change the properties. Let's go. Now, we have to study, we are interested in charge transfer dynamics, charge carrier dynamics, what time scale electron. We are not trying to find out how fast the carriers are produced. That's too fast to be measured. What we want to know, how long this electron, hot electron, takes it to cool down to come to that bottom of the conduction phase. That is what you want to find out. Now, these processes are in the order of few femtoseconds. Now, for the students who have BSc background, you can see that a femtosecond, I am talking about a kinetics. in very short time scale. You know how difficult it is to measure time, even seconds time, our watches will not match. But, I am talking about measuring accurately time of the order of 10 to the power minus 15 seconds. How short this time is, I have given some illustration. Light travels very fast, as you know. It reaches the moon in 1 second. You believe light travels so fast? I give light 50 femtoseconds. 50 femtoseconds, not just 1 femtosecond. I give 50 femtosecond, it travels this much. And what is the width of a human hair? Is only 0.017 to 0.18 millimeter. That means 50 femtosecond is such a short time that light, which takes only 1 second to reach moon, cannot even cross the width of a human hair. So it should give you a feeling of how short a time scale that we are dealing with, accuracy in that time scale. You know that 100-meter race, people will cross this finishing line, and you will have difficulty who has crossed first. We go to camera, we take basically movie camera, then we take the frame by frame, and we see who crossed this thing. Now there it's order of 10 to the power minus 3 seconds. That's the time measuring accuracy camera. And here the accuracy is this. Okay, I hope you got a point. It cannot even travel the width of a human hair. So that is the scale in which we are finding out the things. And we need to have a setup. It's not very easy. It's a complicated setup. A lot of lasers involved in a lot of technologies, and to maintain it is a pain. And particularly in a university system, to create a room, we had to invest a lot of money just a room. The setup, buy all these things will take close to 3 crores. And then room itself will take another 20-30 lakhs. And then temperature has to be maintained, air quality has to be maintained, otherwise the lenses will burn. These are basically highly powered laser. You can see that name. This laser has a name of Spitfire. That means what is coming out is basically fire. If there is a dust particle sitting on the lens will burn. So you have to ensure that you are doing in ultra clean room. You have to take a shower first. You will wear apron, etc. Go through air shower, automatically close. Not more than 2%, because if 3% goes there, temperature will change and then alignment will go. It's a very, very complex system. Okay, and you can see that this is not just a pump-proof setup. This has both absorption as well as emission thing. And this part is called what is called upconversion technique, a fluorescence technique that allows you to measure fluorescence lifetime of 100 femtoseconds or so. But for absorption absorption measurements are much more difficult because they are much more intensity involved. For that you need, this is a seed laser, this is an amplifier, this is basically pump laser, and then this is the amplifier. You get 1064 nanometer laser pulses, 80 megahertz, 30 nanojoule, 100 femtosecond, less than 100 femtosecond. It goes there, and then this one, pumps it, and then what comes out is 4 millijoule pulse. It's a very, very strong pulse, still 1064 nanometer with a different frequency. Then we have basically a setup. This is a component where we basically generate wavelengths. Any wavelength we can want for excitation, 290 to 2600 nanometer. Wherever we want to excite, we can generate. So this is used for excitation of the sample. But you want to record the absorption spectrum, then what you need a white light. That white light we generate from, again, this part, 3 millijoule goes here, 1 millijoule goes here. Then we generate basically, there are materials through which we generate white light, and then we record. This is a very, very difficult setup, and this is a typical picture of the room. Let's go quickly. Okay. Now, again, there is no point in telling me, going to explain how the things are. So we do experiments like this. You can see that these measurements are done from 50 femtoseconds to 400 femtoseconds. Now 400 femtoseconds to 1750 femtoseconds. And then it has gone up to 2000 picoseconds, that is 2 nanoseconds. In other words, we have collected data from 50 femtoseconds to 2 nanoseconds. Now we get this kind of negative absorption, positive absorption, etc. It is an extremely difficult job to find out what these transients are, particularly when you are doing experiments for the first time. when nobody has done that, transients, nobody knows, what these things come from. It is really a painstaking process. It has taken almost 2 years for us to send our first paper on this. You analyze these curves, look at their decay profiles, etc. They are overlapping. You excite at different wavelengths and see, when you excite at this wavelength, you get this. But when you excite at a other wavelength, then you get something missing. So that will tell you something. And now at the end, then again, the transients. It can be electron, it can be hole, it can be an exciton. Now, whether it's an electron and hole, to determine, you have to do control experiments. Uh, you know, you measure basically time profile, how long it comes. We are exciting at different places, and we are seeing how signal is developing, etc. We basically add some reagent like octyl vialogen. This is basically N plus containing quantities pyridinium kind of quantity, bipyridinium kind of thing. It is basically, it takes electrons. So we basically add this kind of electron scavenger to see whether signal disappears or not. Anyway, it's after doing all those things, we come to a conclusion like this. We get a picture like this. This picture tells me that this is CSPB BR3, this is CSPB mixed halide, this is iodide. We know exactly, how long each process, time constant of each processes, where the trap states are, etc. And we also can find out, like, this kind of whole transfer in mixed halide, this kind of, whole transfer, takes place like this. That is the kind of information that we get. Well, that's how you start. But then we also do experiments in which we try to find out how to increase the efficiency. As I mentioned, this is again the solar spectrum, as you see. Now, if one can calculate theoretically, what is the maximum efficiency you can get? That is called SQ limit. Shockley is the limit. Now, what is that limit? Every compound has a band gap, and depending on the band gap, you will have some efficiency. Because there will be many laws. For example, this material, methyl ammonium lead iodide, it has, let's say, band gap of like this, corresponding to this. So anything above is lost because that is will come as a heat, and anything below will not be absorbed. So band gap is very crucial. And according to this SQ limit, the best band gap is basically silicon. They say that the 1.34 electron volt material semiconductor where the gap is this much is the best, and then silica is basically used. You understand why it is close to 1.1 electron volt. So that is closer to that. And so now this is like this. It shows maximum you can get 33%. Now, can we exceed this thing? Now, then we have to basically think, what are the reasons for the losses? Because we are saying if we excite above band gap, then this is the thermal loss like this. If we excite below, nothing is absorbed, that is loss. So what are the, so these are the basically, we can, and also we think that one photon can generate one electron hole pair. Now, can we violate these things? So if we want to surpass or exceed that limit, there are techniques. We try to generate multi-excitons. Okay, different means. We have done that. We have done some experiments. So basically, we give higher energy. We give very high energy. Now, this energy that is coming down, we don't allow it to get lost. But that energy is used to produce another exciton. So this hot electron is coming down here, hot hole is coming down here, but this energy is somehow captured by another particle, and then you have basically electron hole. So basically, you have from one photon you generate, two excitons. So that is not what is assumed while calculating that SQ efficiency. Hot electron capture, as I mentioned, we don't allow it to come down to the ground state. We capture it. We can get more efficiency. And so basically, there are some experiments we have done. Let's not go into this. So basically, it will tell you using this femtosecond, pump probe technique and these perovskite materials, what are the kind of things that we are working on. Very fundamental information and very basic information, but we believe that the results that we find will be very, useful for important, applications. Let me now go to, let me see how I'm doing. I think I have some time. Fluorescence, let me tell you about some fluorescence-based measurements. I would like to show you conventional fluorescence-based measurements. I would like to discuss about single molecule fluorescence technique. See, the fluorescence is such a powerful technique. You can detect a single particle, a single photon. You can be detected these days. It is people say that organic chemists, they say NMR is a very powerful technique, but you see, you need some few milligrams to detect, some characterize a sample. But when you are doing fluorescence studies, you really need. So I'm trying to say that, even one particle will be good enough. And I will tell you, how slow we can go. What is blinking? I am introducing, many of you are not familiar with blinking. And this is, particles, they blink. Most of the particles, whether it's organic molecules, whether it's semiconductors, whether perovskite, they blink. You don't know that. Now you see, this is not my picture, and I have acknowledged where from I have taken, because this looks very good. Say what they have done, they have diluted the solution, very dilute solution. And it is basically immobilized on a surface, glass surface. Immobilized glass surface. And then light is falling on it. You can see that. Look at, focus on this particle, any particle. You see that is coming, this is going. And random. You don't know whether it is going to come back, how long after. These are very random oscillation of on and off state. You can see that. You see also one more thing, what I have indicated as photoactivation. You can see earlier number of particles were less. But as you irradiate the particles, you can see that more number of particles are there. But blinking is very, very clear. This picture is taken through what is called wide angle microscope. Okay. So you see a large area, and then which is irradiated, and see how these things are working. But we don't use this kind of, because their resolution will be less. We do some other experiments. We use confocal fluorescence microscopy. So we see only one particle. Our experiments are not like this, but for visual appeal, this is very, very good. This is very, very attractive. You can see that particles blink. Now, question is, why does a molecule or nanocrystal really blink? Now, you see, if I have a molecule like this with no trap state, or an organic molecule, let's say there is no other state. If you just molecule is going this transition, it will always be on. But the fact is that they have triplet state in molecule, and in other semiconductors, there will be always some trap state. When the molecule is going through this cycle, it is on. But when the molecule is going through this is not emitting. This is basically trap state, non-luminescent, so you don't see that. So that is how it is. So that means, if you can follow the blinking, it will tell you whether the molecule is undergoing this process, it is decaying through this loop, or it is decaying through this loop. It provides some insight. Now blinking, if you want to see, the problem is that you have to go to single molecule spectroscopy. Why? The problem is, if you are dealing with large number of particles and if few molecules are blinking, the problem is the other fluorescent molecules will mask everything. So, but if you have only one molecule, then you can see basically on-off oscillation. So that is why the blinking can be observed only in very dilute condition, very, very dilute condition, when, all particles are separated. You are dealing typically with single molecule condition. If 5-6 molecules are together, you will not be able to see that. So these are very, very difficult experiments to do. What we do, as I mentioned, we don't see like this in a frame. Our signal, what we do, we fix the molecule. I will show you. We fix the molecule on a frame, but we look at, it's called confocal fluorescence microscopy. In this, we look through the molecule through a fluorescence microscope, but we look at only the focal spot. We are not seeing a large area. You're not used to this kind of microscope. When you have done biology experiment or any crystal you are seeing, you see a wide area. But here, confocal microscopy, we see only the focal spot. It's very difficult to see only the focal spot, but not to see the others. That's also a very difficult thing, but that is what you see. And then you can see the fluorescence intensity of a particle. It is like this, and then it goes down, it comes up, and you can see it's a random and oscillation states, on and off state. Okay. Now, this is our typical particle. As you can see, our particles were like this, we synthesized. Then we prepared a solution. We prepared a nanomolar solution, picomolar solution, a 10 to the power minus 12 molar solution, drop casted on a cover slip. We have done this. And then we have created this image by a translation of the microscope. Okay, we have gone through, we have scanned this part like this, and then we have got it like this. So this way we know that there are many particles. Now what we are going to do, we are going to look at each particle one by one at a time. Okay. So what you have seen, we have basically monitored 60 particles. We have seen 60 such particles behavior. And we have seen that 30% of the particles show this kind of behavior, blinking. You can see that. In this, we can see that, it is basically fluctuating like this. But we find that 70% of the particles, show, different kinds of behavior. So what you call flickering. This is blinking. You have clear on state and off state. Here in this case, you have on state, high intensity state, low intensity state, also some, middle state, gray state, I would say gray state. And we analyze them. Basically, we find out the lifetimes decay curves of each level. We plot basically the fluorescence intensity versus lifetime plot and get patterns. I will not go into the technical details. Why this is making a permanent mark, I don't know. So that is what you see. And then we look at basically.
Someone is scratching the screen, I guess.
Yeah, now it is gone. Okay. Yeah. Now what you see that. So we see that a particle is showing that two types of blinking, and then we treat with the ethyl thiol, basically surface treatment, and then we see the blinking, their fluorescence intensity has gone up, it's total intensity, and their blinking pattern, most of them are showing this kind of blinking. You see the range of fluctuation is much less. I have just expanded a particular region, it is 0 to 15 second region. You can see that there is very little fluctuations, and most of them are up. So it tells us basically, again, it's very, very painstaking process to find out what exactly goes on. And then we come to a conclusion like this. I come straight to the conclusion that we see two types of, fluctuations of fluorescence intensity. One is called blinking, other is called flickering. We found out that, blinking is because of something like this, because of a trap state like this. And this, blinking is because of two factors. This is one thing, and this is another thing. This is called OJ recombination process. Let's not, complicate it. Essentially, it says that, when you have one electron already lying there and you have created, another exciton, then what can happen when one exciton recombines, that energy can be used for another electron to go up, non-radiative process. This is called OJ recombination. So we can find out these are the two processes that contribute to blinking, and flickering is caused by, shallow defect surface trap states. That's it. And when we do the surface treatment, what we can do, we can remove the flickering thing completely, but not the blinking ones completely. And the kinetics is dispersive in nature. Well, I will tell little more about one more technique. This is also a single molecule fluorescence-based technique called fluorescence correlation spectroscopy technique, in which this is also called fluorescence, fluctuation spectroscopy. The entire technique is based on fluctuations, something that people hates. But this, if there is no fluctuations, you can't get any information. But the fluctuations should not be random. Fluctuations should be because of one reason. How do you create a fluctuations? When you take a pipette, when you take a volumetric, cuvettes, for example, cell at a fluorimeter, you have a large number of molecules. Even if you have less number of, even if you dilute solution, large number of molecules. So if you want to see fluctuations, your goal is to fluctuations, what you have to do, you have to deal with a very dilute solution, and you cannot see the entire thing. you look at only one small excitation volume. So these experiments are conducted under this condition. You look at the focal spot. A focal spot has a volume of 1 femtoliter, 10 to the power minus 15 liter. It's that focal point. And that focal point also very tightly focal point. It's not like, powerful lens, okay? I think we have a lens that, for which the focal spot is even much less than, volume will be less than 1 femtoliter, okay? And the concentration of the solution is 10 to the power minus 9 molar. And for experiment, you just need one drop. You drop one drop of such solution, 10 to the power minus nanomolar solution, you place between two cover slip and put it in this confocal microscope. That's the experiment. And then you do the experiment. So basically, this is your focal spot. You are looking at this. And since you have placed a drop, the drop is basically these molecules, single molecules are there. They are going through like this. Now, when there is no particle inside, you will see no zero. But when some particle is inside, illuminated region, focal spot, then you see intensity goes up. If there are two particles, then you see intensity goes up like this. So you will see a fluctuation. And this fluctuation is not because of voltage fluctuation or something. This fluctuation is because its particles are diffusing. Yeah? Particles are diffusing. So if you get this, if you can analyze this data, there are standard techniques and get basically the correlation curve, autocorrelation or cross correlation curve, then you get a curve like this, and that time, from that time you can find out how much time the particle has 1 femtoliter volume. That is very important. That will tell you about its volume, radius, and it will tell you about its molecular weight. See, diffusion is not the only reason. There can be some molecules which is diffusing, and in some cases other things are happening. Let's say, for example, when the molecule enters, it is in a free state. Then you have some micelle or something, the molecule gets trapped into micelle. Its fluorescence intensity fluctuates. So there are two factors contributing to that. So then you get a complex curves, and you will get basically, two time constants. One is because long time constant, of course, is because of diffusion, and the short time constant, because during diffusion, some other things are happening. So that part will come here. So you can find out, if you know the reason, what is happening here, a molecule can go from cis-trans isomerization. If that thing happens, then you can get kinetics of that process also. So this is basically a typical process. And technology is this. We have a laser system, and this is my microscope, inverted microscope. And this is my sample cover slip. One drop is there. We are collecting light only from the focal spot. There are many regions, and that is controlled by this small pinhole. This pinhole will ensure that the other regions, light from any other region, you'll see geometry will not permit it to go through this. And then basically you find out correlations. So this is the photograph of the actual microscope. And, there are other things. These are basically the different diode lasers that we can use. And these are basically the couplers in this part, pinhole and etc. like this. And I don't like to go into details like this. For example, when you put perovskites and vary the intensity of the laser, then you see this kind of behavior. And when you normalize this behavior, then you see this kind of curves. And you see that, what you find is that as we vary the intensity, some time is changing, but some time is not changing. That means diffusion time is unaltered, but there is a process which we call, blinking, that is being affected. I think I will not go into the further. Basically, what I wanted to show is the kind of experiments that we do using pump probe and single molecule fluorescence technique. Coupled with, we do also and many other control experiments, ensemble measurements. But all these have become possible because of the students. And it's all started with Nobendu, who came from Kolkata. I don't know, I think recommended by Kamal Bhattacharya. He was the person, who came at a time when we have ordered everything, the components started coming. So he has, from the preparation of the room to the, his CCC was there all the time. And then Apurbo is working on this thing. And now Apurvo is in the finishing stages. Now Somnath is taking over of that thing. On the other hand, if you go to fluorescence correlation setup, there I think in Sudipto, who is now in Sweden, he started this. Then Tasneem, who is be finishing this year, and then now uh, Shumanto is there. So there are others, this Saddam is basically working on deep utility solvents. Sneha worked on, biological eye motifs and G quadruplex, and, who is in Canada. Navendu is in Texas, and like this. So it's all possible because of these students, good students, who were willing to do new stuff. I decided when I did this experiment that I will not do any molecules. When I got femtosecond studies, I said any molecule can be put there and you can get something out of it. Fine. But I will not do this. I will do something very different, which I have not done. Technique will be very different, which I have not used. And the problems also will be very, very different. We have done many other things, zero-dimensional perovskite type materials, etc., etc. And funding, DST was very generous. I think we have got, whenever we wanted money, funding was there. I am in the university system, but I must tell you that these are very expensive setups that I have used, but the money has come from the university because, there are, at the end, in the month of March, there are a lot of money because they have to spend. Whole year they have saved the money and the money is there, you can use. You have a proposal ready, and then at the same, March 15th, finance officer says who has what, then it will be cleared. And there are earlier, the things are gone 5-year period, or 5 years plan period. That 5-year end, in a lot of money, you get femtosecond. Okay, like this. Anyway, I think that's all. Thank you for your attention. Okay, thank you very much. I'll stop here.
Sir.
Yeah. Can I disconnect?
No,
Yep.
sir. Okay.
This money, I mean, slide off slide mode or?
Okay, it's okay, sir. No problem.
Okay. Or whatever you say.
Yeah. Thank you very much, sir, for your spontaneous and really overwhelming talk. Actually, most of our participants are from the undergraduate level, and your talk will really help them out to understand the fluorescence spectroscopy, especially the palm probe portion, palm probe technique of fluorescence spectroscopy, and how the femtosecond is being calculated. All this thing is nicely elaborated by you. So I again thank you from the Department of Chemistry, School of Basic and Applied Sciences at Amherst University. Sir, there are a few questions from our participants. So I will tell you the question one by one. Kindly answer those questions, sir. Karthik Gupta, he is asking a question that why are photochemists not practically effective to produce solar cells which can be used in vehicles?
Which can be used in
vehicles. Yes.
Well, I think the answer is there are two things here. One is science, other is technology. We should not mix up these things. Okay. Say what we are creating new knowledge. Okay. And then technologists use this knowledge to, get something out of it. Okay. Vehicles are there. There are vehicles. I can tell you these Mahindra vehicles are there. Mahindra, I have driven a Mahindra vehicle. It's a very silent vehicle, fully, it's a battery operated. Okay. Now that is charged again by solar light. So it's not electrical things, this kind of things are there. It has not come into the market as yet, but with time, as the price of petrol goes up and the other cost goes down, that is what you are going to see, sooner or later.
Thank you, sir. Next question by Tonmoy. What is the better route to prepare semiconductor nanocrystals from the perovskites? Hydrothermal, soil states, or soil gel method?
No. Say perovskites are semiconductors. Okay. Perovskites are semiconductors because their energy gap is such, they fall in that semiconductor band gap region. Now, I mentioned it is basically what I discussed three methods. One is they're all known as hot injection method. I'm not synthesizing, say, when you are trying to synthesize bulk materials, you can go for sol gel, etc. But when if you are particularly interested in nanocrystals, where you have to control the size and quality of the particles, you can't go for any other thing. The best method is, what is called, basically hot injection method, but with 3 precursor method. When you are using bulk thing, any method you use, there are so many methods, that I mentioned also. This, precipitation method also should be fine. But if you want to well-defined, well-characterized nanocrystals of good quality, there is no other way. You have to use through hot injection method. Sorry, hot injection method, yes.
Sir, another question by Kirti Alam. Does the blinking phenomenon have biological application? Does the blinking phenomenon has the biological application?
Well, I have not explored any biological application of the blinking thing, but one can possibly. I can give you an example. For example, let's say I take either cadmium. I don't have to take perovskite. I can take cadmium selenide, which are robust material, very photostable, and I put it at some biological site, and uh, if I analyze this blinking pattern, it may be I may be able to get some information. I'm not sure. This is very difficult because you see, scattering is really a problem in blinking. And biological system, when the particle sizes are bigger, they will give more scattering. Okay, so that you have to see, scattering, etc. If you can avoid, then something can be. These are interesting things. These are. I think blinking thing. I will not think so much about applications. These are new kind of experiments. That should, enlighten you. You should feel great. What is the new technique?
Yes, sir. Thank you, sir. Another question by Deepak Kumar. How do you make single molecule or single crystal? Or how do you control its kinetics?
The dilution. I mentioned that I showed you this, 2 kinds of blinking. One is in frozen solution, and I told that you have a picomolar solution or femtomolar solution, very dilute solution, and spread it and then light it. There is no guarantee that it will be a single molecule thing. But when you get blinking behavior, then you surely know that these are blinking behavior. Say one negative thing about fluorescence spectroscopy is that the resolution in fluorescence spectroscopy is not as good as electron microscopy. It's just because of the wavelength. Okay, say it's lambda by 2 resolution. That means if you are using 600 nanometer light, then 300 nanometer is the resolution. So any smaller particle will look 300 nanometer. Okay.
Yes, sir. Sir, this is the last question. That is why halide perovskite or lead-free halide perovskite prepared in the nitrogen atmosphere, why not in ambient condition?
See, even when we say we have to see, say, ambient condition when you are going to do these, most of these syntheses are, I mentioned, hot injection method. Now you have lead. Do you want to generate lead oxide? Nobody would like. So basically, you have to have basically inert atmosphere, even to prepare, not lead free. Even to prepare, lead halides, you go to inert atmosphere under nitrogen. Nothing very difficult, nitrogen atmosphere. That's it. Okay, oxygen should not be there because they will form oxide and create problems. Material will not be pure.
Okay, thank you, sir.
I have a question. This question is, you're talking about single molecule spectroscopy. What about single cell spectroscopy? Many people are doing single cell, and these days, if you want to characterize more like COVID-19 or what is it possible to do something in a single cell? People are doing some single cell, I guess.
I have no experience. I think it is possible, but I will not be able to tell you, how to look at this cell. But people normally also use, they
this confocal microscopy,
fluorescent probe and etc. They can use separate a single cell and then study this. Should be easy because cells are much bigger than these particles.
right. That's what I mentioned.
Because they're micrometer size, and here we are dealing with a nanometer, less than 10 nanometer in most cases.
Okay. And this perovskite has any kind of application like an imaging technique or whatever?
Yes, they're very, LED light thing is they're luminescent. Their main drawback is their stability towards these polar solvent. So they are salts, they will dissolve. So that's the main problem. Otherwise, in the dry condition, they are fantastic. They are very, very stable, and their fluorescence quantum yield is close to 100%. There are so many blue range, green range, yellow range, red range, 100%. So they are very, very, LED applications, photo detectors, lasers, everything is coming that side also. Apart from the photovoltaic side, where we try to convert, solar energy to electrical energy, this optoelectronic application, they have huge potential. Though initially it started for some other photovoltaic applications, but later people have realized that that is also very, very important.
So in solvents, they are not stable at all, right?
Solvents means, most of the studies have to be done. You can see that, I have used basically octadecene, that kind of hydrocarbon solvents, toluene, etc. Okay.
Yeah.
So that is an issue, and that is what people are trying to, for applications, they're trying to put some coat of some materials, PMMA, etc., like this to stabilize, etc. A lot of attempts are there to stabilize this perovskite in nanocrystals.
Okay, thank you, Anunoy. Over to Arpan.
Yes, sir. So this is on last question asked by one student actually. His name is Tomal Pal. So he has cited one of your journal in scientific report that you have showed different morphology using different anti-solvent.
Yeah.
What is the scope of ethyl acetate as anti-solvent?
Well, these are very specific things, that, anti-solvent, say basically I mentioned, good solvent, bad solvent, anti-solvent. Now that again, that synthesis they were looking for, that is not basically the nanocrystals. That is not nanocrystals. They are bulk materials. They are bigger size materials, and that is why anti-solvent precipitation method can work. But if you want to prepare nanocrystals, where size you have to restrict to certain range, because if you want 7 nanometer, then you get blue. If you go to 9 nanometer, then you get red. You have to control the size very, very carefully. Then you have to go for this. Where your aim is just to prepare, different shape micro discs or micro size things, then there are so many methods are available. I told actually in response to an earlier query, that is very, very easy.
Thank you very much, sir. Now the question answer session has come to an end. And
Before that, Arpan, I have one thing to say.
okay, sir.
Yeah. I thank Anunoy first of all, and then today we have Dr. Arpan Manna as the head of the Department of Chemistry, and he was selected by you. Arpan probably knows.
I remember
You came to our campus and
Yeah.
you selected really a person who is so dynamic and active. We are very lucky to have Arpan running the department very, effectively and all.
Good to know that. I
Yeah.
think we selected one more person.
Rupam
You
Sen.
remember one more
Rupam.
person? He is also very good. Huh?
But
His,
yeah,
his,
Arpan
his
was the
name is
first person.
Topto Kanchan.
Right, Tapta Kanchan
Topto
did not
Kanchan.
join. Did not join. Yeah.
He is
We
now
offered him.
he is now in IIT Jammu. Central University of Jammu. Central University of Jammu.
Okay. We offered him. He didn't come actually.
No,
That's
I
it.
think some issues were there. Let's leave it. I know he was also a good candidate. Okay.
But Dr. Arpan Manna, for information, is selected by our speaker today, Anunoy Samanta. Yeah. Arpan.
Thank you very much, sir.
Okay.
Now, the vote of thanks will be given by our colleague, our faculty member, Dr. Deepsika Bhattacharya. So over to Deepsika Madam.
Thank you, Arpan. On behalf of our department, I am very much thankful to Professor Arunoy Samanto sir for accepting our invitation in his busy schedule and presented such a wonderful webinar. Thank you for this nice experience, sir, what we have gathered today, and followed by the fruitful interactive session. I am also very much thankful to our Sanjeev Ghosh sir, Professor Sanjeev Ghosh sir, and Professor Bimal Kumar Sarkar sir for their constant support and arranging this wonderful webinar. And I am also thankful, immensely actually grateful and thankful to Dr. Arpan Manna, who is our HOD and who is actually arranging all these things and constantly supporting us through this difficult situation. And also, I am thankful to Dr. Prantik Banerjee for conducting this webinar so nicely. Finally, I am sincerely thankful to my colleagues, faculties, and participants who are here today for their cooperation and patience throughout this webinar. And one thing I have to mention that there is a feedback form which will be sent in 2 hours to all of you. Please take your time to fill it up and send it back to us through our email ID. And last but not the least, we are extremely thankful to our Honorable Chancellor Sir, Vice Chancellor Sir, and Adamas University for providing us this platform to execute, to conduct our seminars. Thank you.
Thank you, sir.
Okay. I can disconnect now. Thank you very much.
Thank you, sir.
Thank you very much.
Welcome.
Thank you very much.
Thank you, Arunoy. Stay safe and stay healthy.
Okay, sir.
Okay.
Hmm. এখনো আছিস কিছু বলবে?